Hello, this is Jack Jackson. Let's look at a couple of more examples of computing arc lengths. So we introduced this in the previous video. Now it's your time to practice a couple of examples. So here's one for you to try. What is the length of the arc along the curve of f of x equals the natural logarithm of the cosine of x from x equals 0 to x equals pi over 4? So your turn, work this out yourself, and then come back and check it against the solution here when you're finished. It's a good chance for you to practice a little bit. Press pause now. Okay, well, now you're back. I hope this means that you've tried this yourself. It's always useful to try problems yourself first. So we know f of x is natural logarithm of the cosine of x. We're going to need to find the derivative. Well, the derivative of log of u is 1 over u, so that's 1 over cosine of x, times the derivative of u. Derivative of cosine x is negative sine x. Sine x over cosine x is tangent of x. So f prime is just the opposite of tangent of x. Next, we want to square that. And if we square that, the negatives cancel, and so we get tangent square, and we want to add 1 to that. So we need 1 plus the derivative squared. But 1 plus tangent square is just secant square. That's our basic Pythagorean identity for secants of tangents. And so we get that. Then we take the square root of that. We're looking at the absolute value of secant of x. Square root of the secant square of x is just the absolute value of secant x. Now, on the interval from 0 to pi over 4, secant of x is positive, so we can drop the absolute value. And furthermore, secant of x is continuous on that interval, so we're going to be able to use the fundamental theorem of calculus to work this out. So the arc length is, in general, the integral from some x value to lower x to upper x, the square root of 1 plus f prime of x squared. So we decided that this whole integrand is just secant of x. So we're just integrating secant of x from 0 to pi over 4. Well, secant of x, an antiderivative, is the natural logarithm of the absolute value of secant x plus tangent of x. We evaluate from 0 to pi over 4, plug in pi over 4's here, minus, and then plug in zeros. Secant of pi over 4 is the square root of 2. Think of that as in a triangle of sides of length 1, 1, and square root of 2. The angle would be pi over 4. And so the secant of that is hypotenuse over adjacent, which is square root of 2 over 1, which is square root of 2. Tangent of pi over 4 is just 1. That's the same triangle. That's opposite over adjacent. 1 over 1 is 1. Secant of 0 is 1. Cosine of 0 is 1. Secant of 0 is the reciprocal of that, which is still 1. Tangent of 0 is 0. 1 plus 0 is 0. 1 plus 0 is 1. Absolute value is 1, and the logarithm of that is 0. So this last part is going to go away. Square root of 2 plus 1 is positive, so I can drop the absolute value. And our final answer for the exact length of that curve is the natural logarithm of the square root of 2 plus 1, or approximately 0.88 as we plug that in the calculator. There's more digits there. So here's a picture of it using my Arclength GeoGebra app. So you can see that there, and there's the decimal approximation there. And the TI Inspire does it exactly. I took natural log of cosine of x, stored that as f1 of x, so it would graph this right here if I go to the graphing window, and chose the appropriate size window. And then we know that it's the integral from 0 to pi over 4 of the square root of 1 plus the derivative of f1 of x squared. So find the derivative, square, add 1, square root, integrate from a to b. And we did that, and that turned out to be natural logarithm of square root of 2 plus 1, which is about 0.881373588702, accurate to that many digits on the calculator. Now, notice that in the Inspire, I could let it do the derivative and do the integral as well, let it do all the work. I just have to remember that this is how we set the thing up. In fact, you could actually define a new function on the TI Inspire called Arclength, where we input a function and some limits, and it will compute the arc length for you. It would be too hard to set that up. All right, here's another one for you to try. Find the length of the curve y equals x to the fourth over 16 plus 1 over 2x squared from x equals 2 to 3. Set up the appropriate integral for the exact value and then use a calculator to approximate the arc length. So don't worry about finding the value exactly this time. Do this one yourself. Press pause now. Okay, so here it is using the app that I have. This is what the graph looks like, and this is the arc length we're talking about right here, going from 2, 1.125 to 3, 5.11806 approximately. And so there is the graph that what we're looking at. It says it's about 4.13. Here's how we could do it here. Couple of different ways we could do it. I went ahead and found the derivative here. Y is 1/16 x to the fourth plus 1/2 x to the negative 2. Then dy over dx, let's see, 4 times 1/16 is 1/4, goes down to the power of 3. Negative 2 times 1/2 is negative 1. Subtract 1 from the power, it becomes negative 3. So there's the derivative. Take that, square it, plus 1. I put that in the calculator. So I did the derivative by hand, but let the calculator do the rest. I could even let the calculator do the derivative as far as that goes. And it came out with an exact value of 595 over 144, or exactly 4.13194, and then the 4 repeats forever. Even with the TI-84, we don't even have to find the derivative. If we put the function in as y1, we can say, do the integral, in this case from 2 to 3, of the square root of 1 plus parentheses the derivative of y1 with respect to x, and then the part that's running off the screen here is there's a square and then a dx at the end. And it's just doing a numerical derivative, a symmetric difference quotient, to approximate the derivative. Then it's using a numerical integral, something like Simpson's rule, to approximate the integral. So it's doing approximations within approximations, and yet it still gets a pretty good answer. It's accurate to five significant digits. 1, 2, 3, 4, 5. They both round off to a 9 right there. And it's almost right to the next digit. That's a 4, which is correct. That would actually round off to a 5 instead. So I would say this is a 5 significant digit approximation. Almost a 6 significant digit approximation. So pretty good, considering this way we didn't have to actually find any derivatives or integrals. The calculator did all the work for us. So, you know, there's a couple examples for you to do. Time to go practice some homework problems with Arclength and get better and better at this process.